from background. I'll now pass over to Alex, who'll give a bit of a more detailed look into the data and metadata that sits behind this, so we can start to work out what kinds of things that we can work with. Once again, for those who joined late, please use the Q&A section to ask questions. We've also got a couple of people in the room here with us, so they can feel free to pop up whenever they want. So, Alex.
Thanks, Phil. And hello, everybody. I'm going to go through a few things here, starting with Geoscience Australia's metadata index, which identifies where you can access Digital Earth Australia data. I'm going to talk a little bit about a tool, the Open Data Cube, that you can use to access the data, and then we'll shift over into demonstrations of the use of the Open Data Cube. So I'm going to share my screen here. All right. So Phil's got the metadata page open here, and so this is one of Geoscience Australia's tools to examine what data is available, including a lot of data from Digital Earth Australia. So in this tool, if we search in the box here for Landsat, the first item that comes up is a product called GeoMedian, and this is a product which is a derivative of Landsat data. What it takes is, for each pixel in a satellite image, it stacks them all up together over time and takes out the median of that pixel. And so it's a median over a calendar year. This means that it gets essentially something like the average pixel, so it excludes the outliers like cloud. What I want to show you here is that down the bottom of this page, there are links out to the catalogs where you can actually access the data, or a web service built on top of the data. So, for example, there is a Threads catalog which accesses the data from the National Compute Infrastructure. And what we're quite interested in is Digital Earth Australia's new offering, which is data hosted directly on Amazon Web Services S3. So if we drill through here, Phil, and find a product, so L8, Landsat 8, and a tile, and you can find an index for these tiles in a number of ways, but we just pick one at random. And pick a year, so 2016, and there's an arbitrary date here. What we've got now is a piece of metadata in the YAML file at the bottom there, which describes the tile, the extents, and other important metadata, boring for humans, important for machines, and it also holds a TIFF for each band that's available. What's quite interesting about this is that it represents the use of a new paradigm, which is that these TIFFs are not just regular TIFFs, they're cloud-optimized GeoTIFFs. So if we can move through the slides now, Phil. Instead of downloading each of those GeoTIFFs and storing them on a file system for use in your application, what you can do is actually just grab the URL for one of those and load it into an application like QGIS, and it will stream data straight off the cloud without you having to download the entire file. Just in brief, a cloud-optimized GeoTIFF utilizes a reasonably new HTTP function, which is a range request, which allows you to request a part of a file rather than the whole thing. And the GeoTIFF is structured in a way that you can read the header of the GeoTIFF and understand what's inside it. And tools have been written now that allow you to stream parts of even an enormous GeoTIFF up to hundreds of gigabytes without quite seamlessly. A lot of people are using this paradigm, such as Mapbox here, who have an example using Lambda and Raster.io to stream data out of cloud-optimized GeoTIFFs into tiles. But other organizations such as Planet and Digital Globe are storing their data on the cloud as cloud-optimized GeoTIFFs. Now, the good news for us is that COGS are supported natively in the Open Data Cube. So we can actually index, which means store a reference to all of those TIFF files in the Open Data Cube's index and use them on the fly. So what is the Open Data Cube? According to the Open Data Cube website, the objective of the Open Data Cube is to increase the impact of satellite data by providing an open and freely accessible exploitation tool, and to foster a community to develop, sustain, and grow the breadth and depth of applications. Now that's a lot of words and it means some nice fuzzy things, but in a nutshell, the Open Data Cube is a Python library that facilitates working with raster data and, to a large extent, Earth observation data. Technically, the Open Data Cube, once you implement it, is comprised of three parts: the data, the infrastructure, and applications on top of that. So when it comes to data, I guess the old paradigm is downloading a whole bunch of data from USGS or from Digital Earth, from Geoscience Australia, putting them into a file system, and you usually need a really big one, and then using it from there. But if you use the modern paradigm of cloud-optimized geochips and cloud storage, such as S3, you can leave the data in place. You don't need to sort of grab it and own it yourself. You can let someone else, the custodian, keep maintaining it. Then we have the infrastructure, so the Python library itself of the Open Data Cube and a Postgres index. So what we do is we index all the data, or wherever it is, whether it's a file system or on the cloud, and store a reference to that in the database. And that means that the application layer can then query through a standard API, which is the Open Data Cube library, and discover what data is available, metadata around that data, and also actually access the data. So it abstracts the complexity around going and getting a bunch of files and working out which ones are in your area of interest and pulling out the data and making it consumable. There's a number of things you can build on top of the Open Data Cube then, whether it be a sort of bespoke API that does some kind of function, or Digital Earth Australia has a number of spatial web services such as WMS that are streaming these cloud-optimized geochips and rendering them and making them available in a web mapping framework or desktop application. But what we're going to be demonstrating, just as an example of the use of the Open Data Cube API, is a number of Jupyter notebooks. For those that aren't aware, Jupyter is a data science environment, and we'll talk a bit more about that shortly. So from here, I'll hand back over to Phil, who's going to give a brief demonstration of an application of the Open Data Cube, and soon after that, Felix is going to get deep diving into technology.
So what I'll do is I'll show, again, for those who were part of the previous webinar series, the example will be the same. I'm only going to show one example of basically a clean, finished product of what happens at the end of the Jupyter notebooks, but then unlike last time, I'll then hand over to Felix, and then he can go through all of what sits in the background so that A, you guys can understand how to use and redeploy them, and B, you know where to go to do that. So jumping straight over into this example. I'm not going to load this in real time. What we're going to go through is essentially so this is an example of a Jupyter notebook. It is a combination of, I guess, a wiki style of text that allows you to explain concepts, provide links, videos, and images, and then executable lines of code that you can use to then demonstrate the concepts you expand in the document part of the notebook. This particular example is a mining example where essentially mining companies need to pay a certain amount of money into a rehabilitation fund each year based on the amount of land that they disturb. As they close down a mine site and rehabilitate it, in theory, that amount of money that they pay into that fund should decrease, but they need to measure the amount of disturbed land so that they can work out how much they need to pay. At the moment, that's done using surveyors and ecologists that go out kind of once a year on a consulting basis and measure. And while that's completely fine, it means that if an event happened 11 months ago that you could have corrected, you missed the opportunity to minimize the impacts of that, and you end up increasing the amount of rehabilitation funds that you need to spend. You also don't know when in the year a particular disturbance happened, and it also gives you a way to validate or sanity check the results that come back from the field. In terms of how Digital Earth Australia is going to be useful for this, in here, Felix will show you how to select your own study areas. In this one, we've pre-selected a study area over a particular mine site, and I have loaded in about 400 different scenes of imagery over about a 5-year period that overlay this mine site. I could do that in real time, that's fine. It takes about 90 seconds, which isn't long for all of that data to be indexed and stored and spun up with a visual interface. But during a live demo, that feels like forever, so I've pre-canned it here. Essentially what we're going to do is have a look at the data over time to have a look at how our rehabilitation efforts are going. So the first line of code here loads the case study. It says, my case study is over this area. I want data from the Landsat data product store, and I want it over this time period. That did that. then running this fractional cover line application tool, then pulled all that data into, I guess, a data cube over this little area, which I can now use to interrogate data. So sitting behind this interface is essentially the queryable data cube. So what we can do is draw a simple polygon. Again, this is purely a demonstration purpose. This is to inspire people as to what is possible to do in this. This is not a production-ready application. This would never go out to an end user. This is to help educate people as to what's possible so that you can include it in your own applications. But essentially, we will, draw our study area, which is our current mine site, and that goes and creates a graph that just worked in real time over 5 years of analysis of data every 2 weeks, which is then aggregated into monthly time points to have a look at the amount of bare earth, which is the stat that we're interested in for disturbance, and then the amount of green vegetation and non-green vegetation that's part of this, as well as the amount of water, so we can see if there was any flooding incidents or anything like that. This in itself is not useful because it doesn't give us a reference point. So what we can also do is create a little study area over to the west, which represents a more natural condition. And now the two results are graphed together. Our mine site is in blue. Our native vegetation area is in orange. And what we can see is 5 years ago, there was a big difference with the amount of bare ground exposed compared to a natural area. And over time, as that mine has rehabilitated and vegetation has grown, that gap has closed to where we are now, where it's actually starting to look somewhat similar. So this is a good news story about metrics. But what we could have found is if we were monitoring this on a monthly basis and there'd been a spike or deviation for a couple of months, we'd get a trigger to get out to that site early. Again, many of you have seen that example before. That's where I'll finish things. What Felix is now going to do is then dig into what happens behind that. So I'll just try and share screens to new share. Yeah, actually, if you can request it, it'd be great.
Got it. Done. Thanks, Phil, for providing that demonstration. I'm gonna jump straight into the code and what's happening under the hood of demonstrations such as the one that Phil just gave, and I'm going to go through what is actually happening under the hood, and then I'm going to demonstrate some of the notebooks we've prepared using this technology. So first off, I'm just going to request a Sentinel-2A product over a latitude and longitude, and ask for five measurement instruments: red, green, blue, near infrared, and a cloud mask. And so while this is executing, I'd like to describe exactly what it's doing here. So even though we call it the Open Data Cube, it's actually more of an Open Data Cube. Every one of the measurement instruments that I've requested is its own cube, like in this diagram, and they're linked together by a latitude, a longitude, and a time dimension. And so it doesn't matter what resolution the information you're asking for is in, it will resample it into the cube that the ODC constructs. And as we move back up, you can see that that query has just finished, and it's taken 35 seconds. And I'd like to emphasize what it's actually done there. It's gone to the S3 data store and pulled out 11 times 5 geotips. So that's 11 times 5 is 55.
Go to data scientist.
Yeah. So it's opened 5 files, and it's resampled them and put them into this standard format of the data cube. Now, the kind of operations on these cubes that I'm going to describe are more of an exploratory nature, but I would like to say that they can be expanded out to supercomputing. For example, the algorithms that Geosciences Australia has, such as the Digital Earth products like fractional cover and WAFs, they've been calculated on the NCI using data cubes. So you can use these tools to explore your data, and you can also use them to do continent-wide analysis. So next I'm going to talk about querying a data cube. And you can query a data cube using either a pixel drill, slicing, or with masks. But essentially, once you have a cube, you could construct any kind of 3D object made up of mini cubes, which are pixels from that object. So I'm going to, so for example, a pixel drill, traditionally that's been used to explore land change over Landsat pixels. So you would get 20 years, 30 years of a single pixel, and use certain algorithms to detect changes that have occurred on that pixel. From a data cube perspective, it uses a Python library called Xarray, and I've got a link up here that you can click and find out how to master the Xarray. But so the pixel drill is the first operation I perform here, and I'm doing it using an index within the cube. So I've got a value for the 500th pixel and the 1000th pixel, and that's giving me a pixel drill through time, which is the first kind of lot of Xarray that you see there. And as you can see, the dimensions are 11 and 1 over a single pixel. You might also notice that it's an array, so I can type in a multitude of coordinates in there, and it'll return multitude of pixel drills. In the second example, I've got, rather than using indexes, I'm using the actual coordinate system that I've requested the data in, and it's picking the pixel that's nearest to that coordinate and performing the same pixel drill. The second type of operation you can use to sculpt your cube as such is a slice, which is giving it 2 coordinates to request data from. So in this example, it's asking for all the data between pixels 200 and 300 on both the X and Y axes, and for and a slice at the third time interval. And that's this cube here. And that's as you can see, it's just a 100 by 100 pixel, sorry, not pixel, array. And so running these is quite seamless. All right. So next, what can you do once you have the data in the cube? You can plot any of these variables. So any of these measurement instruments. So we've got near infrared. That's just a quick plot. You can plot them all if you like, just to see them in any kind of ad hoc manner. And some of the other stuff you can do is, if anyone's ever used the pandas library, you can do operations that are very similar to what you would do in pandas. And those who haven't used pandas, it's very similar to what you can do with Excel. So, for example, in this first line of code, I'm grouping all within the pixel drill into rather than individual flyovers. I want to see the data on a monthly basis. and I've done a monthly means. And you can group by any of the dimensions, and you can create custom group by functions. For example, you can do every 3 days, every 4 days, every year, every 2 years. The second one I've got here is I'm going to turn that slice that we extracted above into a cross section. Cross sections in remote sensing and I guess data analysis are a good way to measure structures. So you can do cross sections across a river or a canyon, and they're very useful in that regard. And so I'm creating a cross section out of our slice and asking it to give me the means of all the pixels that are across that slice. And at the bottom here, I'm visualizing the near infrared band on for that data request. Now sorry?
That shows a river?
That doesn't show a river. That actually just, you'll see what it shows soon, but it's an area of Tasmania. Alex always seems to slip Tasmanian case studies in our presentations because that's where he's from. So in the second slide, I'm going to be using, I requested the F mask, which is a DEA product for creating masks over your requested data cubes. QA, which is a quality assurance. These normally, if you're using Landsat, these come as big pack combinations representing surface, atmosphere, sensor conditions, and generally speaking, they describe the usefulness of a given pixel. So like this specific mask, which is made for Sentinel-2, it has, for example, as you can, in the bits, there's 0 representing no data, 1 representing valid data, 2 representing cloud data. And what I'm going to do out of this is I'm going to create a clean pixel mask in which I extract only the valid pixels from the data cube that we've requested. And so here I've run it, and you can see that it's just like the data cubes. It's the mask is also cubes that you can just overlay onto the main requested data cube. And so we'll visualize some of that. So this is number 9, time slice number 9. And wait a second, I haven't run that. So this is good to show that we are doing all this live. And I need to actually run the cells rather than talk about them. All right. And see what this looks like.
So what I might mention here is that this is time slice 9, and it just so happens that we've got 11 time slices over Tasmania, and time slices 1 to 8 actually have like 99% of the image covered in cloud. And so, so when you actually get the clean pixels out, you're left with about 4 of them. This one here is actually Tasmania on a not very cloudy day.
But if I go through some of those other time slices, the quality of the image is very different. All right, that's a terrible one. So when you filter out the artifacts, you're actually left with nothing. And this is also why you might want to group by month or use mosaics in general, so as to get the best pixel on a monthly basis.
Number 9.
So I'll go back to number 9, just to show that Tasmania can be clear on a good day.
So what this is showing is the image, the raw image, and then we can use the QA layer to mask out the areas that are definitely cloud or have other issues, or cloud shadow as well.
Cloud shadow, saturation, or a number of other instrument errors. So the second thing I'd like to demonstrate is the ability to merge multiple cubes. And this can happen on a number of occasions. For example, the case study that Phil had demonstrated where the fractional product was used to interrogate the mine side. What was actually happening behind was that we were also requesting the WAFS data set, which is water observation from space, merging them together into a single cube and filtering out any section that was wet, because fractional cover does not work over water. But what I'm going to do in this example is I'm going to load data from Sentinel-2B, which is Sentinel-2A's twin satellite, and this will extract data over another 11 time slices. So one of these satellites flies at over every 5 days. So it's either Sentinel-2A or 2B, and in this case, we're going to combine them together into a single combined cube. So while this is happening, this is going to take 30 seconds. This can be actually very useful to create multi-source cubes. So you could almost create a Landsat cube of 5, 7, 8. Sentinel, create some kind of indices, some kind of coefficients to like narrow in those wavelengths and have a very extensive cube. So now so that's finished, and as you can see now, there's 21 time slices in that cube that we had prior. So these are the operations that you can do with the ODC library on actual data. Now the other element to it is performing these operations on finding it. So one of the most difficult things that I've found is knowing the metadata that you're searching, so knowing your case study area. And in the examples that we've created, we've got an interface where we link Google Maps to a case study area, but the Open Data Cube API is also able to access a lot of the metadata that comes with the data cube. And the metadata in its own can be very useful if you're also building applications that want to consume the cogs in its own way. So what I'm going to do is I'm going to run through this notebook. And so the first metadata command that you can run is list products. So this command will show you, will create a Python table in which you can view all the products that are indexed in the cube. So for our ODC instance, we've got one running on Jupyter Hub, and these are the products that we've indexed. And this contains information about the format of the files, the coordinate system, the resolution, and a bit of metadata. Now this is at a product level. You can also, if you have a large cube and you have a lot of derived products, you can of course just find the products you're looking for. And then you can, there's also metadata attached to each measurement instrument. And so in this cell, you can see that the Landsat 5 fractional cover, these are the variables attached to it. And so these commands are very useful when you're thinking about what's the name of the instrument that I want to interrogate, what's the metadata associated to it, and what metric is it in, and what resolution it's in, and you can view that information there. You can also test your query that you're performing. So here I've just given it once again another XY latitude and longitude over Tasmania, and I'm asking it what data is available over a specific time period, and that returns 4 data sets. Those data sets can be further interrogated for metadata, and there's a massive list of information that you can extract from there. So I'm just going to ask for the date of the flyover, the unique identifier of the data set, and the bounds that it's in. But essentially, when you're using the cube and you're creating any kind of derived products, you can create your own metadata. In the case of DEA products, you'll be consuming DEA's metadata in the format that they have it in. Another example of actually querying, and so this is an example of what's in the DEA metadata. You have so very similar to the product definitions above. And each one of those data sets can also be queried for what are the files on S3, where are they located, where's the metadata file. So this will point you to the directory structure that Alex demonstrated in his demonstration, and the location of each one of those geotips.
I guess what I might like to emphasize just here, if I can step in, Felix, is that when Felix wrote the query right at the start of his demonstration, where he said, load the data for Sentinel for this lat long bounding box for this time constraint, the Open Data Cube refers to this metadata to say which files are available for this bounding box on this time, and it knows how to go and extract the data from them all. And so as Felix said, that initial data cube load, which was 11 time slices, went and grabbed data out of 11 times 5 geotip files stored on S3 and pulled it all in, and in 30 seconds had that data ready to do the analysis in. And so it's pretty easy to see how streamlined getting data off these files is. You don't even need to,
particularly compared to how we click through it.
Yeah. But particularly compared to if you want to go and click through and work out which path and row the file is and download all the geotips and load them in a desktop GIS and have a look at it and make sure it is the area of interest you want, and then combine them together with raster algebra and then start doing. Now, if you compare it to the desktop GIS paradigm, this kind of data science and the Open Data Cube API makes all of this working with vast quantities of data seamless. One more point I'll make is that the data that's indexed in this data cube here, it covers the entirety of Australia as well. So we could actually change that bounding box to anywhere in Australia and pull the data in. And it'll still only take 30 seconds.
Which is a good time to show how to use our notebooks, because since we do have all the data indexed over Australia, we've organized our notebooks into defining an area of interest, and using this page here, so I can zoom out from here. So what this application is doing in the background is it's using the metadata querying that I've demonstrated and applying the load for the of the cube and doing a bunch of slices, trims, and statistics over the and graphically representing it. So look, I'll just zoom into anywhere. Let's, for a change, go somewhere sunny as opposed to cloudy. So we'll take Queensland, and I'll zoom into here. So we plan to make these this Jupyter Hub accessible to everyone. So you can log into this Jupyter Hub. You can look at some of the examples I've shown. You can look at our sample applications, or you could just play around with the DEA data, the data cube, anywhere you like. If you'd like some assistance, do let us know. So I'm going to request all the data there is over that region, and this is just a more easier user interface to show me what's available there. So the way we've organized our Jupyter notebooks is we've got macros running, so you can type in any of these macros here into a cell, and it'll load one of our apps. So for example, this is this Sentinel. I could load the geomedian. I think we spoke about geomedians, but we haven't seen them. And so this will request the yearly geomedians that Alex was showing in the product description earlier. And here we go.
And that just loaded 30 years of geomedian data?
Oh no, that's just on Landsat 8.
Yeah. Oh, just on Landsat 8.
Yeah, but I can do the Landsat 7 app also, but and as demonstrated before, you can. This one just explores geomedians using indices. So you've got a bunch of indices above here, and you can interrogate them using polygons or points.
So since that's loaded the data cube at this arbitrary location that Felix selected, the data cube is in memory, and the polygon there has then gone through and gotten a mean. Is that right, for each time step of that geomedian?
No, it's just a derived band indice. So in this case, it's been an NDMI, which is a moisture index, and that was for the polygon and the points.
So a straight read from the.
But I think more importantly, I'd like to come back to the few points I made at the start of the presentation. I think the demonstrations I've given really kind of show that this is a shift in paradigm. So we're not accessing massive scenes. We're requesting small scenes through latitude, longitudes, and time. The output of our data request is a simple, standard, and extensible way to interact and perform analysis on the data. And it allows users to define exactly in what state data is to be delivered in terms of projection, resolution, bands, and data sets. And it's got enough tools to easily create subsets of derivative products that are managed and tracked by the ODC, and provides a base set of functions and tools that make analysis more simple.
Excellent. Thank you very much, Felix. So we're now going to, I'm going to hand things back to Alex, who'll take you through Cube in a box, which is something that we've created to try and make things a little bit easier.
Thanks, Phil. So at this point, I can hear all of you crying out, but how can I do this? This seems all very abstract. And what we've put together at Frontier SI is a way that you can run the Open Data Cube on a laptop or on AWS if you've got an account there. So Cube in a Box is a method of wrapping up the Open Data Cube and its requirements in terms of a system to run the library and Postgres database using Docker and Docker Compose. We've got a GitHub repo where you can go and view this and have a look at how it's all put together. You can run it locally using Docker Compose, and so on a laptop, start it up. It also runs using a CloudFormation template so that you can, with one click and a tiny bit of configuration, launch it on AWS, and it'll automatically index and prepare an environment over a case study area. So what this enables is really simple evaluation. It allows you to sort of get set up and testing really easily. It allows you to do development if you're into that, and we've used it to reproduce bugs or issues in the very rare case that you find those. It just sets up a rapid evaluation environment. So some of the enabling technology here is Docker itself and Docker Compose. Jupyter, which is what we've been showing before for the notebook environment, so for the data science, the exploration. It uses cloud optimized GeoTIFFs, and currently the Cube in a Box reads from Landsat 8, which is a global data set. So you can actually put your own regions of interest anywhere in the world and have an Open Data Cube up and running in minutes for that area, or in hours if you pick a really big area. It uses GDAL and raster.io, which is what the Open Data Cube uses to access the data, PostgreSQL, and obviously the Open Data Cube itself. Now, running the Cube in a Box locally, on the video on the right, this shows how fast it is to start up the Open Data Cube. You need to have Docker running and Docker Compose, but that's it. And in that amount of time there, we've got a brand new Open Data Cube environment where you're ready to start indexing and analyzing data using Jupyter. As I said, it uses Landsat 8, so you don't have to download the data and store it on your hard drive. You can just point it at a region of interest and index it and get it ready to go. We also have a way to run it on the cloud. So we have a CloudFormation template, and if you go to the GitHub, there is a link there which you can click, which will actually launch the CloudFormation template into your AWS account, and you get to choose how big the EC2 instance is and your region of interest. And it takes around 3 minutes to deploy and 5 minutes to index the example region of interest that we have. And so in around 10 minutes, you can have your Open Data Cube to start exploring. In addition to that, we've got the sandbox environment, which is in a testing phase at the moment here for Frontier SI. And the sandbox there is what we've just used to demonstrate. So all of the examples that Felix went through, you can actually log in as long as you have a GitHub account and explore them now. So with these two environments, the sandbox, where you don't even need to install anything, you can just go to a website and launch it, and Cube in a Box, where you need to have a bit of technical nous, but no complex sort of Python library installed and set up. We can get up and running in a very short amount of time and start exploring the Open Data Cube and exploring Digital Earth Australia data.
We'll have that in about a week, I'd say. Yeah,
so we're currently at the moment working on Cube in a Box and pointing it at Digital Earth Australia data itself, but there's very soon we'll have that running. The Jupyter Hub environment, the sandbox, works already with Digital Earth Australia data.
Yeah.
So with that, I'll hand back to Phil, and we'll shift over to a Q&A session, I think.
Yeah, no worries. So just before we go to the last point on there, everything that we've been demonstrating with Felix has been based on Amazon for those government or academic people online that have access to the NCI. Geoscience Australia have a very detailed user guide, GitHub and Jupyter Notebook on how to deploy and run analysis using the NCI as well. There is a slide that I forgot to copy into this, but I will put into the deck before we distribute this to everyone via email after the presentation, which covers the support channels. So there is various email addresses to anyone that's been part of the presentation team today, as well as to the Geoscience Australia team. There is a Open Data Cube Slack channel, which you can use for generic Open Data Cube questions, but there are also individual channels in there for Digital Earth Australia specifically. And there are a range of other resources that we'll point people to as well. And the presentation from today will be distributed, and the recording from today will be put up on YouTube for those that want to slow things down and go through again step by step, because we've covered a fair bit of information. So on the fact that we've covered